Hello and welcome to Space Moth. Today we'll be learning about stellar evolution. In this video we'll cover several things, including the triggers of star formation, the births and deaths of stars, the formation of a sun-like star, and the formation of massive and smaller stars. Essentially, a star forms when part of the interstellar medium collapses on itself. But what causes this? Well, there are several things that trigger the collapse process. Shockwaves from nearby stars, for example. Or, perhaps, the death of a nearby sun-like star, also known as a planetary nebula. It could even be the result of a supernova or even a galaxy collision. So, let's say that one of these events occurs and a star formation is triggered. What exactly happens? First, you have the cloud of interstellar gas and dust. These are incredibly vast and usually have temperatures of about 10 Kelvin. Despite its low temperature, it still maintains enough internal pressure to resist gravity. However, once one of the aforementioned triggers occurs, the equilibrium is disrupted and the interstellar cloud begins to fragment or break up. Once the interstellar cloud begins to fragment, it shrinks substantially. Its temperature increases to around 100 Kelvin, and its density increases. Eventually, it becomes too dense for radiation to easily escape, and fragmentation ceases. At this point, the fragmented cloud is around the size of our solar system. The interior is much hotter and denser than the exterior, and it begins to resemble a star. This is called a protostar. The protostar continues to shrink, becomes denser and hotter, and at this point its core is around 1 million Kelvin. You can also distinguish the photosphere here, or the part of the star that emits the light we see. Calculating the luminosity using radius and temperature, we find that its luminosity is several times that of the Sun. Luminosity is measured how much energy is radiated from a star. Its luminosity is so high because it is also several times the Sun's size. Now that we know its temperature and luminosity, we can plot our protostar on the Hertzsprung-Russell diagram, or the HR diagram for short. The HR diagram is a graph that plots luminosity on the y-axis and temperature on the x-axis. The motion of the star across the HR diagram throughout its life is known as the evolutionary track. As the protostar continues to contract, it rotates faster and faster to conserve angular momentum and flattens out, becoming a protostellar disk. However, the protostar is still not in equilibrium, so it continues to contract. Throughout the next few stages, the protostar will move down and to the left on the HR diagram as it decreases in size and increases in temperature. This is known as the Hiashi trap. The protostar is now well on its way to becoming a star. Its luminosity and size are both around 10 times the Sun, and the core temperature is around 5 million K. However, this is still not nearly enough for nuclear fusion to occur. Congratulations! 10 million years after that baby cloud started to fragment, you finally have an official star. The core temperature is 10 million Kelvin, which means that nuclear fusion can occur. Although, it's still not reached the main sequence yet. Don't worry, it will, probably. Double congratulations! Your star has reached the main sequence. The main sequence is the part of the HR diagram where a star spends around 90% of its life. The star is in hydrostatic equilibrium, a balance of outward pressure and gravity, and will stay here for millions and millions of years. After the star goes through its main sequence portion of its life, it undergoes lots of changes in the last stretch of its life. The star goes through core hydrogen burning, slowly depleting its hydrogen supply and increasing its helium concentration. Because the core is too cold to fuse helium into anything heavier, the hydrostatic equilibrium is disrupted and the helium core shrinks. This allows for more nuclear fusion and the energy is increased, increasing the outward pressure and swelling the star. The hydrogen in the outer shell is now burning more rapidly than before, and the star enters the hydrogen shell burning stage. Throughout all of this, the temperature decreases and the luminosity increases. The star, at this point, is called a subgiant. This hydrogen burning process continues, and the star continues to increase in size. The lower temperatures lead to opacity. Convection used to transport these massive amounts of energy mean that temperatures remain constant throughout stages 8 and 9. The star, which is now a red giant, is running out of time. If hydrogen burning continues like this, then the core will eventually collapse. However, this is when things get weird. The core is now 10 to the 8th Kelvin, hot enough for helium to fuse into carbon. In a process called the triple alpha process, helium is fused into beryllium, which is fused into carbon. Like hydrogen, the rate at which helium burns increases with temperature, so at very high temperatures, the helium doesn't last very long. The now carbon core doesn't burn, so it continues to shrink as the hydrogen and helium in the outer layers continue to burn. This second descent to the giant branch is called the asymptotic giant branch. The carbon core is now too dense and small to continue to contract and shrink. As the core burns its last remaining fuel, the outer layers expand and cool, creating a planetary nebula. In creating this planetary nebula, the interstellar matter around it is disrupted and can possibly give birth to new stars, thus maintaining the cycle. Now, the carbon core at the center of the nebula has a very high temperature and a very small size. This gives it its name, white dwarf. Finally, after 13 stages, the star's evolution is over. The white dwarf continues to burn and expel its radiation until eventually all that remains are dim embers. This is known as a black dwarf. But all of this is only accurate if your star is similar to the Sun. So how does this process change if your star is bigger or smaller? If your star is smaller than 0.08 times the mass of the Sun, then it can't go through nuclear fusion. It's simply not hot enough. If this is the case, your third star will be becoming a brown dwarf, similar to a planet, but bigger. If your brown dwarf is less than 12 Jupiter masses, it will be considered a planet. The more massive a star, however, the faster its evolution is. This is because its large size forces it to burn fuel much faster. High-mass stars only significantly diverge from low-mass stars after they leave the main sequence. In many high-mass stars, helium burning occurs smoothly, not undergoing the explosion called the helium flash that sun-like stars go through. Because of this, there is only one ascent to the giant branch, rather than two. The red giant continues to swell until eventually it explodes in a brilliant flash called the supernova. In this episode, we learned that stars form when the interstellar medium collapses on itself, about the 14 stages of star formation, that small stars become brown dwarfs, and that large stars become supernovas. That's all for today. See you next time on Space More.